And thank you. Welcome, Math 13 students. This is our final presentation for the semester. We're going to finish up our review of the entire semester. So tonight we'll look at 8, 9, 10, 11, and 12. I've put together a series of examples, and we'll run through that right now. So come with me over to my other screen, and we'll get going. I have taken the liberty of inputting some of this data directly into my calculator just to save a little bit of time. And we'll go on from there. So here's our final exam review. I did leave the vocabulary off of this last little bit of review. I really wasn't referencing it much, and students have access to that anyway. So here we go. I'm going to start with chapter 8. I do not break out the sections individually, but they essentially go in order. So as I say, we'll look at 8, 9, 10, 11, and 12. And I'll begin with chapter 8. And again, my desire here is not to reteach the course, but to really kind of hit the high points, go over the tools and the keystrokes that we'll need. So chapter 8. And I'll remind you before I begin that 8.1 kind of threw everything on the everything in the shop at the wall, and you encountered pretty much all of that as you went through the material. But I always get the impression that 8.1 can be overwhelming, and the important stuff tends to get lost. What do I really want students to be able to know how to do out of 8.1? There's really only one thing. Directly, and that's working with the p-value. And I'll remind people that a p-value is a value that is designed to determine the outcome of a hypothesis test. It's calculated using the test statistic and the type of test, left, right, or two-tailed test. It's an area, the p-value, so it's going to be a probability, and it's compared to that level of significance alpha. So one of the things that could have you do on your exam is to calculate a p-value. If you have a test statistic and the hypotheses, the p-value should be possible to be calculated. And I'll note that if it's a left-tailed test, the p-value is the area to the left of the test statistic. The right-tailed test, the p-value is the area to the right of that test statistic. And the two-tail test, the p-value is double the area that you might find either to the left or the right of the test statistic, depending on the side. So let's take a look at an example. We have a claim that more than half students will take English 1A this semester. And this claim and the data produced a test statistic of z equals 1.8. Find the p-value. So to find the p-value, we need to make sense of the hypothesis. More than half, that's p is greater than 0.5. That means I'm looking at a right-tail test. Now that area, the p-value is equal to 0.0359. How did I get that value? I will remind you that to find an area or a probability, when we have a normal distribution, we use the normal CDF tool. So let me go ahead and switch over to my calculator. Oop. There we go, distribution. Normal CDF. The lower bound is 1.8. The upper bound, in this case, it's 10 raised to the 9th power. The mean is 0. The standard deviation is 1 because we're working with the z distribution. So there's my p-value, 0.03593 and change. 359 to 3 significant digits. So that area there is a 0.0359. And we use it says normal 83 there. This is an older presentation when I was using some different tools. It's the normal CDF. Now, once we got the notion of a hypothesis test and the p-value nailed down, I started to ask you guys to conduct tests of hypotheses. They all had the same 5 steps. We used the p-value process for all of our serious problems. So let's run through an example where we use the p-value approach to test a claim about a population proportion. This is the type of problem you would find in 8.1. So we have a recent poll of 830 randomly selected individuals. 185 had 1 or more tattoos. We want to test the claim that the percentage of individuals with 1 or more tattoos is less than 25%. And we'll use a level of significance of 0.05. So less than 25%, that means P, the proportion, population proportion, is less than 0.25 in decimal form. For the p-value, I will use the one prop z-test, and I will compare the p-value to the alpha of 0.05. I will reject the null hypothesis when p is less than or equal to the alpha. So let me just pick up the numbers here. 185 out of 830. Okay. So let me jump over. My calculator, and I'll pick up the one prop z-test, p naught 0.5, excuse me, clear, 0.25. We had, what did I say, 175 out of 830. Let me just double check that. $185 out of 830. It's very hard for me to look at both screens when I'm doing the share, so thank you for your patience. So go back up here. I said it was 185. Yeah. $185 out of 830, less than 25%. It is a left tail test. Now I can go ahead and calculate the p-value. I'll get the test statistic also. So I see a 0.356 and change, and that's my p-value. Very similar to that other problem we just looked at a little bit ago. Probably use the same numbers. So there it is, 0.0356. I compare that to 0.05. It's distinctly less than. So we will reject the null hypothesis. So the initial claim, the claim was less than 25%, is supported at the alpha equals 0.05 level. You'll note that we always end up with addressing that initial claim. So you have to identify whether the claim is the null or the alternative, and then whether the claim is supported by the data. And I will note that the p-value is an area, and that significant level is an area. And again, I cannot stress this over enough. If the p-value is less than that area, then we get to reject the null hypothesis. So you see that test statistic of -1.804 that we pulled from that previous hypothesis test. There is a critical value for an area of 5% on the left, -1.645. And you can see distinctly here that that test statistic falls in the rejection region, which should indicate to all of us that in this pretty picture, it's fairly clear that the p-value is less than the alpha in terms of area. Now, that brings up the question, though, what happens if we change the alpha? I mean, alpha is brought to the problem by the researcher. If we consider that example again, and we test the claim with an alpha equals a 0.01, did the outcome change? Well, the outcome was changed, because when we reduced alpha to the 0.01, it became more difficult or harder to reject the null hypothesis. So I took the liberty of putting in a picture of the distribution. I've got my alpha 0.01, that's the gray over here, and then we've got our test statistic in the area of 0.0356. You can see that this area here is bigger than the rejection region. So we fail to reject the null hypothesis in that regard. That was 8.2, claims about a proportion. Next up was 8.3, claims about a population mean. So we have a simple random sample of 78 cars on a local fee rate. It produced a mean speed of 46.1 miles per hour, a standard deviation of 7.3 miles per hour. And at the alpha equals 0.05 level of significance, we want to test the claim that the mean speed is more than 45 miles per hour. And we'll do that using the t-test. You really need to be able to pick up on the fact that we have a claim about a mean. So mu equals 45 miles per hour. Mu is greater than 45 miles per hour. And I will note that the alternative hypothesis is our initial claim. Now I've got my p-value here. Let me run over to my calculator. And pick up the, oh, there we go, t-test. I have summary statistics. The mean was 45 miles per hour, the null hypothesis mean. We had 46.1 miles per hour for my sample mean, 7.3 miles per hour for the sample standard deviation. We had a 78 for our sample size. This is a right tail test, greater than 45. I'll pick up the p-value, and there's the 0.0936. If I round that little guy to 3 significant digits. So that's what I will compare with my alpha. And once again, there's lots of video available on the Canvas site showing these keystrokes, as well as this video once it posts, I suppose. So 0.0936, that's greater than 0.05, so we will fail to reject the null hypothesis. So my initial claim of the mean greater than 45 miles per hour is not supported at the alpha equals 0.05 level of significance. Now, I'll ask a follow-up question here. Is there a level of significance alpha that would cause us to reject the null hypothesis? Let me jump back one screen. There's my p-value. I would need an alpha that was at least as large or larger than that. Yeah. P equals 0.936, or in terms of a percentage, 9.36% of the area underneath that little distribution. So a significance level of 10% would cause us to reject the null hypothesis and validate the claim of 45 miles per hour. See, the important thing to remember is there's no one hard and fast answer to any one of these hypothesis tests. It's only answered in terms of a given alpha. You change your alpha, the outcome could change. And remember, the outcome is a probability expression, really. So it doesn't guarantee anything at all. As the commercial always says, your experience may be different. But it's a leg up. That's why we use it. So that was chapter 8. Now we're into chapter 9. 9.2 and 9.3. So the first step is we're going to test a claim about 2 population means. We use independent samples, and we do not pool those 2 samples. You may remember the notion of pooling, and I'll show you the pool button in a moment, and I'll tell you to stay away. We have two distinctly different regions here. There should be a little bit more to the story, honestly. They measure the hours of high-speed wind. If you're going to build a windmill for power generation, you need to have lots of wind. If the wind never blows where you live, there's no point in building a windmill. So, region A and region B, 14.2 versus 15.6, mean hours of acceptable wind time. Standard deviation, 3.1 and 4.2 hours. We sampled 37 days for region A and 43 days for region B. We're going to test the claim that region A has fewer number of acceptable hours per day than region B. Which region gets the farm? So let's go ahead and go over this test. Let me come back here and note those particular values. Hold on. There we go. Two sample t-test. We have data. So let's see. I'm not sure what you're seeing on your screen right now, but this is what I need to do to get my data into my calculator. So 14.2 hours, 3.1 hours, and 37 days for sample 1, 15.6 hours, 4.2 hours, and 43 days for sample number 2. All right, so let me stop my sharing just to make sure we're all on the same page. I get a little confused sometimes with this sharing screen. I'm not quite sure what you guys are seeing. So there's my calculator. There's the data that goes in there. We want to test the claim that there are fewer days in region number 1. So that is mean 1 is less than mean 2. It is a left tail test. We do not pool, and there was never any reason this semester to change that. And now we can go ahead and calculate. So there's my p-value, 0.0456 and change. I get a summary of my data points, by the way, so I can see if I've entered things in correctly. Hopefully I have. So now if I jump back to the presentation, we're going to test the claim that region A has fewer acceptable days. So the test produces a p-value of 0.0465. Actually, I think it's 456. I think that's a typo. And that's less than 0.05 either way. So we would reject the null hypothesis, the claim that the hours are equal between regions A and region B. So the conclusion would be that region B has more acceptable hours of high wind for us to use with our wind farm. And this really is how statistics is used in the real world. It's usually very messy. There's never any really clear answer. And you just do your best and realize that when you work with a probability, there's a chance you're going to be right eventually, and there's a chance you're going to be wrong. Sometimes it's hard to figure out which even occurred. The world is messy. So claims about two population means when we have independent samples and we do not pool those guys. Now, the other type of question that we encountered is the question where we're comparing dependent samples, where there's, say, a before and an after, or some really clear relationship between the two samples. In this example, we have an English instructor who wants to see if a new grammar method will reduce the number of grammar errors. So we have some before and after data, and we want to test the claim that the new method is effective in reducing grammatical error. And we'll use a 0.05 level of significance, and there is the data. So this is the number of errors before and after. Somewhere between the before and the after is when the students receive this new training. First person, 12 to 9. they improved. The second person, 9 to 6, they improved. The third person, oh, they were perfect. Now they're making mistakes. So their error rate actually went up. And not everyone's always goes down, but there we go. That's the before and after data. Now, the trick with this is to recognize you've got dependent samples and to realize that what you'll need to do is to address the claim by finding the actual difference and working with the difference. That's the real data set. So the claim is to lower the error rate. That means the difference between before minus last should be positive. Now, before I go any further with this, let me just jump over to my other calculator, or other screen, I should say, and take a look at this problem. I took the liberty of inputting that data into my calculator already. So list 1 is the before, list 2 is the after data. What I need to do is to find their difference. So I highlight the list name, second L1 minus second L2. Now, what I want to do is I want to address that difference. Since the difference is positive when the method has improved the score, I need to keep that in mind. So now, let me jump back to my other screen for a moment. And the null hypothesis here is that the mean difference is 0. In other words, the training doesn't help or hurt. The alternative here is, since we want to show improvement, that means a lower score the second time, fewer errors, if you will. We want that difference to be positive, just like in that first pair of numbers. So it's important to remember that this is one of those data sets that require us to use raw data. I want to point my calculator at list 3. And to remember that this is really a one population test. There's not 2 populations here. There's only a single populations of difference. Honestly, this topic should be an 8-point something or other. So there we go. We have raw data. That data works with the null hypothesis of 0. The data is in list 3. And we want to be greater than 0 for a left tail test, right tail test. And now I'll calculate my p-value. I get a p-value of 0.0378 when I do my rounding. So 0.0378 is less than the 0.05. We will reject that claim. So the initial claim is supported at the alpha equals 0.05 level. So yes, it does appear to reduce error, and the instructor will probably use it again next semester. Now let's talk about chapter 10. Chapter 10 had 2 sections we took a look at, 10.1 and 10.2. They went together, and honestly, a single set of keystrokes handles both those chapters. So I put all of this together into a single example. And this is really probably the one type of question that really requires a lot of calculator interaction. I'll remind you, chapter 10 was the topic of linear correlation and regression. So we have a claim and we have some data. We have a random sample of statistics students, and they were evaluated on the number of homework problems completed and the associated grade on an exam of the same material. I would hope that more problems done in homework would mean a better grade on an exam, but we'll see. There's the data set. It's a little long, 12 pairs of data. I didn't have room to make one long XY list, so I doubled it up. The X's are problems completed. The Y is the exam score. And then the first thing I'm going to do is to generate a scatter plot. So let me come over here and pick up a calculator. Now, I already took the liberty of inputting all of that data there. So list 4 and list 5 are the XY data for that problem set. And I'll remind you of the keystrokes for the scatter plot. I need my stat plot. Plot number 1 needs to be turned on. And I need to make sure I select the scatter plot. I also need to point it at the correct data if I haven't used list 1 and list 2, and I didn't here. I'll look at purple or magenta, I guess. And then the most important key in that key stroke series is the zoom stat. This will guarantee that you can see your data set. And you can see there's a general linear pattern, if you will, from the lower left to the upper right. More homework problems up here, higher scores on the exam up here. So, keystrokes for the data, for the scatter plot for our data set. And there it is. Now the test part. We want to test the claim that the number of problems completed is correlated with exam score, and we'll use a 5% level of significance. The 5 steps. Let me get it all up here, actually. I'm not sure why it came up so weird. Now let me jump over to my other screen. So list 4 and list 5 is where that data lives. Somewhere down near here at the bottom. Linear regression t-test. The X, second list 4, the Y, second list 5. Frequency is 1. This is always a two-tailed test. We leave the regression equation blank and we calculate. I get a lot of stuff on this screen because it handles both 10.1 and 10.2. What I need here for my test is my p-value, the 0.00379 when I do my rounding. Is that what I have on that other screen? Yes. So there's my p-value, 0.0379. That's less than 0.05, so we will reject the null hypothesis. So there's enough evidence to support the claim that rho is not equal to 0 at the alpha equals 0.05 level of significance. That means the correlation is useful and the problem sets can be used to estimate exam scores. And that's where I'll need the rest of that data. You'll note that the first thing on the linear regression t-test output screen is y equals a plus bx. That is our regression equation. And we'll want to round the coefficients to 1 decimal place. And I picked them right off of here. It's important to remember that the format here is different than the y equals mx plus b that I am sure you remember from your algebra course. So the y-intercept is 43.1. My slope b is 0.4x, and what you see here. So there's the regression equation. I'll plug in an x and I'll use that to estimate a y value. For 70 problems, I'll round that to the nearest whole number. The estimated exam score would be 71. The arithmetic there, by the way, is really straightforward. People usually just put that directly into their calculator, the 43.1 plus the 0.4 times 70. No order of operation issues or anything like that. But you got to put it in the correct order and do the rounding correctly. So that really is chapter 10 right there. Chapter 11. 11.1 and 11.2. This is where we took a look at the good fit test, the multinomial experiment, if you will, and then the test for independence between row and column variables when we had a contingency table. This was also the chapter where we encountered the chi-square distribution for the first time. And every test in this chapter is a right tail test. The chi-square only has 0 and positive values. And if there's enough mismatch between the numerator and the denominator of a funky fraction, if the numerator is big enough over the denominator, if you will, then we reject the null hypothesis. That makes them all right tail tests. So here's my example. Reducing industrial accidents is the goal of current research. So below we have some data on accident counts by day of the week. We want to consider the claim that accidents occur with equal frequency throughout the week. So there's the data. Looks like Monday is a clumsy day. But that's just the way it looks. We're going to bring statistics to bear upon this problem. So what I need is not just the observed frequency, but I need the expected frequency. If we're going to assume equal frequencies, we need to find that expected frequency for each category. We had a total of 85 observations. And let me back up a screen. The big mistake students make with this type of problem is they'll jump directly to the test without taking the time to add up the total number of observations. So 29 plus 15, 16, 12, and 13 get me to a total of 85 observations. If we're going to assume equal frequency, those 85 observations are distributed equally each day of the week. 85 divided by 5 means I should be expecting 17 accidents each day of the week, if they're to occur with equal frequency. So what I need is both of these data sets. This is what needs to go into my calculator. So let me stop my sharing here and jump over to my other screen. And I'll need 2 lists. I'm done with my first list. I'm done with my second list. I'm done with my third list. And I just need my first and second list for observed and expected. So let's see, we have 29, 15, and 16. Then we have 12 and 13. 17, 17, 17, 17, 17. Yes, over and over again, 5 times over. Equal frequency. That's what we would expect. So let me just make sure we're all on the same page here. I apologize for this. I honestly can't see what you see. So there I have it. We've got the observed in list 1. We've got the expected frequencies in list 2. Now I go and pick up the good fit test. The chi-square good fit, not X, chi-square. Observed is in list 1. Expected is in list 2. Ah, the degrees of freedom. You need your number of categories minus 1 or 4. So I get a 0.02465 So that's a 0.0247 for my p-value. So the null hypothesis, the claim of equal frequency, and by the way, if one wanted to write equal frequency there, that's fine. 0.0247 is my p-value. It's less than the 0.05. We will reject the null hypothesis, so that initial claim of equal frequencies is not supported at the alpha equals 0.05 level. So yeah, it does appear that some days do have more accidents than others. I will point out that the test does not tell you which day or days have more accidents. Honestly, if you look at the data set though, with 29 accidents on Monday, it was like more than 10 more, I think, than any other day of the week in that data set. So that's probably the odds-on favorite to be the most deadliest day at work. Now, the second example I have comes from 11.2. We have categorical data on parent and child smoking outcomes. Both parents smoke, one parent smoked, neither parent smoked. And then we also have data on the children smoking. Child smokes, child does not smoke. So this is one of those two-way contingency tables. And I'll need to note the number of rows, 3, number of columns, 2. And we are going to test for independence between the row and the column variables. That means there's no connection, which kind of goes against my gut feeling, which tells me that if parents smoke, the kids are more likely to smoke. but that's just my gut. So we want to test the claim that parent and child smoking are independent. We want to use an alpha equals 0.05 level. So let me stop my sharing. Actually, let me go back one screen because I'm going to need that data. And let me pick up my calculator. And I will remind you that for these problems here, we need to work with a matrix. So I need second matrix to bring up the matrix tools, and I will want to edit matrix A. That matrix that I saw in that problem had 3 rows and 2 columns. Remember, in math land, it is always row first and column second. So there's my data. Now I need to go back into the example and pick up that data. So we've got, let's see, we've got 400 and 1,380, 416, 1,823, 325, and then 1,168. Now, one of the nice things about that particular tool is that I can go directly to the test from the matrix. So matrix A, there's my data. I go directly to stat, scroll down to my chi-square test. Matrix A is the observed matrix. My matrix B will be my expected matrix. Unlike 11.1, I do not need to supply expected values. I just say calculate, and my calculator will go out and build the correct matrix B with the correct size and populate it with the correct values. So there's my test outcome. There's the p-value, 0.00506 with rounding. This is truly a straightforward test if you can get stuff into the matrix. Sounds like a movie thing. So to test that claim, the claim is that parent and child smoking are independent. That's the null. Parent and child smoking are dependent. There's a 0.00506, is less than the 0.05 by a goodly margin. We will reject the null hypothesis, so our initial claim of independence is not supported at that level of significance. So yes, it does seem as if there does appear to be a relationship. Again, it doesn't really tell you the direction of that relationship or the nature of it, but again, it can be intuited from the, or interpreted and guessed at pretty accurately from the way the numbers flow. Now, we get to our very last section, chapter 12 and 12.1, our ANOVA test. This is another new introduction. We use what we call the F distribution here. We honestly don't spend a lot of time focusing on that little subtlety, but I will point out that the F distribution is somewhat similar in some sense to the chi-square distribution. 0 or positive values only. And all these tests, again, are right-tailed tests. So, in assessing student outcome, it is important to consider student subpopulations. Students who take morning classes may differ from those that take evening classes. We want to use the given data to test the claim that classes come from populations with equal means. There's my class 1, there's my class 2, there's my class 3. So those are exam scores from 3 different classes, random selectively sampled students. And it's a very, very straightforward problem to recognize because it's the only one we encounter all semester that's got 3 lists of numbers that we have to deal with. So let me go ahead and take a moment to get that into my calculator. I need 3 lists. And we got, for the first one, list 1. List number 2. All right, so there's my data. I got a problem somewhere with my data. List 1 and list 2 should not have the same number of numbers in it. Let's see. Oh, there it is. So try that again. There we go. Now that looks a little better. And then let me just double check one last thing. There should be one more number. Okay. All right. So I have my data in there in list 1, list 2, and list 3. So it's important to remember where you put your data. You're going to have to point your calculator at all 3 lists. So hold on. Where'd you guys go? There you are. Try that again. There we go. All right, so list 1, list 2, and list 3. ANOVA, very last test on the list. Very end of the semester, it's fitting. So, second list 1, comma, second list 2, comma, second list 3, close them up. Got to remember the commas, otherwise you'll get an error message in Cursor Calculator. And there we go. This stuff gives you a lot of extra stuff. That's a wonderful jumping off point for a more advanced statistics course. For us, we need the p-value, 0.00549 and change. So notice how I've written my null hypothesis. We're going to test that they come from populations with equal means. mu1 equals mu2 equals mu3. At least one is different. We rejected the null, so the initial claim, which was the null, is not supported. That does seem to indicate that at least one of those populations is different. Maybe all 3 are different from each other. Maybe 2 pair up. But it's important to note that the ANOVA test does identify means as being different. The test does not really distinguish or tell you directly which of the population means or means may be different. Further analysis is usually required. Usually what we do is we pair things up with a t-test. There would be, let's see, I think 3 t-tests we would need to do. We have to compare 1 and 2, 1 and 3, and 2 and 3. And then we can tell. So there we go. And that really brings me to the end of my presentation as far as the review goes. So I'm also just about out of time, but I did get it all in. That was good. So there we go. Let me stop the recording.